Hello. So now we're doing applications of trig, differentiation, which hopefully you've gotten used to the fact now that this basically means tangents and normals and things of that nature. So, find the equation to 2 sin x where it's pi over 6. Alright, so tangent. We still follow exactly the same process, which is to say we find the derivative, we find the point, and we put it all together in the equation of the line. Okay, so derivative. So the derivative of sine is cos, remembering that sine goes up, so it's positive cos. So at x equals pi over 6. Get ready, I'm going to ask you to tell me what it is. Okay, if you were able to beat me to that, go and get yourself a chocolate. You've done well. If you weren't, you should be ashamed. And when x equals pi over 6 as well, y equals 2 sine pi over 6, which is so therefore the tangent is y minus the y coordinate equals the gradient outside of x minus 6 coordinate. And realistically, that's probably how you stop, because now you've got root 3's and pi's, so it's not a nice, you're not going to be able to simplify it at all. Okay, so find the equation of the tangents and normals to that curve and show that the lines that are formed form a square. Sketch the square and find the other two vertices. Alright, so I'm just going to start by drawing something, because immediately there's a lot of stuff going on. So here's the curve, so that's pi over 2, that's minus pi over 2, and you can actually kind of already see what's going on. Tangents will look something like this. The normals will then look something like this. This is B and this is A. So basically I need to find these 2 points, and I'll just need to show that the lines are all kind of perpendicular to each other as well. Okay, so let's do A first. So, well, we could just do the derivative first, couldn't we? So dy dx is minus sine. So for A, at x equals minus pi over 2, the gradient of the tangent must be minus sine of minus pi over 2, which is minus 1 times minus 1, which is 1. So therefore, the gradient of the normal is minus 1. And we also need the y coordinate. Oh, well, we know the y coordinate is 0. Right, we're told here. So therefore, the tangent is y equals 1 x plus pi over 2. So y equals x plus pi over 2. And the normal, we just replace the 1 with the minus 1. I didn't leave myself enough room. That's okay. So there is the tangent and the normal. And then we could just do B in the same way. So the gradient of the tangent is minus 1 times sine positive pi over 2, and that's minus 1. So the gradient of the normal, whoops, is positive 1. So the tangent is y equals negative x minus pi over 2. Negative x plus pi over 2. And the normal is y equals positive x minus pi over 2. So they're clearly all perpendicular, and we basically need to work out where the lines meet. Okay, so I'm going to call this point here point C. I'll call this point here point C, right? So to find C, so that's the tangent at A, so that's this line here, and that's the tangent as well, and the tangent at B, so that's this line here. Right, so these two give us the coordinates for C. So clearly x must be 0, meaning y must be pi over 2. Subbing it back into either of them. And then for D, it's the two normals, so it's this one and this one. And you can probably already see that what x is going to be 0 again. Okay. So how do I show that they're a square? What do I have to do? Well, it's kind of obvious now. I could then say, therefore, diagonals bisect at right angles. Because look at the diagonals, it's this line and this line is the axes, and you've clearly cut them in half. Therefore, it's a square. Okay, can't be a rhombus. It's a square. Because diagonals bisect in a square, diagonals bisect at right angles in a rhombus. Okay, there's example 1. Pause if you need to. Example 2. Find the equation of the tangent. Alright, so y dashed is 2 sec squared 2x at x equals pi over 8. I can feel you all getting nervous already as I ask you to do the exact value for me. But we actually did this yesterday. Sec squared pi over 4 is 1 on cos squared pi over 4, which is 1 on root 2 squared, which is a half. And y is tan, 2x on 8, which is tan pi over 4, which is 1. So therefore, it's y minus 1 equals 4x minus pi over 8. So it's y equals 4x minus pi over 2 plus 1. That's the equation of the tangent. Find the x-intercept and the y-intercept. So when x equals 0, y equals minus pi over 2 plus 1. And for y equals 0, pi over 2 minus 1, so x is pi over 8 minus 1 over 4. So that's the x and y intercept. Sketch the situation. Sure thing. So here's the tan function. And because it's tan 2x, the asymptotes are now at pi over 4. I'm talking about this point here at pi over 8. Here's my tangent. So this point here is pi over 8 minus a quarter, and this point here is minus pi over 2 plus 1. Okay, they're the x and the y intercepts respectively. So then find the area of the triangle. That's easy, it's half base times height. Alright, because there's a right angle there. One of them is a base, the other one's a height, doesn't matter. So area equals a half. Just rewriting it so it's obvious that it's positive. Oh no, I was wrong, Dr. Emmanuel. So that's the absolute value of negative pi over 2 plus 1, which we must now make it positive. Donezo. Okay, lastly, curve sketching. Consider this curve. Okay, so part A. So it's got a limited domain from 0 to 2 pi. So when x is 0, y equals 1. When x equals 2 pi, y also equals 1. In both cases, cos is 1, sine is 0. Find the x-intercepts. 0 equals sine x plus cos x. Pause and think before I tell you the answer. But the answer is, as usual, we subtract cos x across over here. Divide by cos x. Normally don't divide by variables. But if cos x is 0, we know sine x is 1. Right? That's all minus 1. That's from the unit circle. Because cos x is 0 here. And that's when sine x is 1 or minus 1. So it's fine. Whenever dividing by 0, this equation has a solution. So therefore, on the left-hand side, it's actually minus 1. So x is, so in the domain, tan being minus 1 is only over here, I think, isn't it? All stations to central. Couldn't have been more wrong. It's actually here and here. So that's 3 pi over 4 and 7 pi over 4. Stationary points. So y dash is cos x sine x, and that equals 0. When I do exactly the same thing I did before, I end up with positive tan x equals 0. So 1, because I add sine x across, and then I divide by cos x. So that gives me x is pi over 4, or 5 pi over 4. And in those cases, y is 1 on root 2 plus 1 on root 2, and negative 1 on root 2, negative 1 on root 2, respectively. So the stationary points are pi over 4, 2 over root 2, which is just root 2, and 5 pi over 4, and negative root 2. Finding points of inflection. So this alludes to what we just did at the end of yesterday's. So the second derivative is negative sine x which will get to 0. We did that before. Back here. And so we get 3 pi over 4 and 7 pi over 4. And then we would test. Okay. So x, y dot dot. 3 pi over 4, 7 pi over 4. So here you could do pi over 2, here you could do pi, here you could do 2 pi. So the second derivative at pi over 2 is negative 1. Here it's 0. At pi it's positive 1. So I'm just substituting into this, right? Not the equals 0 bit, just this. 7 pi over 4 is 0, and then 2 pi, it's negative 1. So yes, they're both inflections. Okay, so the inflections are the x-intercepts. And then I try my best to draw this. So here's my 1, here's my 1. I got x-intercepts at 3 pi over 4 and 7 pi over 4, so here and here. I've got turning points at pi over 4 and root 2, which is up. Sorry, I forgot to determine their nature, but this, when I do it, will be a maximum, and this will be a minimum. So you'd have to test it. in the second derivative. Sorry about that. This video is getting too long already. So, something like this. Inflection point, like that. Don't know if you can hear Griffin in the background, but he's going crazy. Okay, and there's the curve. Which we chuck in Desmos as well and make sure it made sense. It's pretty poor scale, isn't it? It's a little bit better. Okay. Alright. Homework's over here somewhere. There it is. See you later.